So yeah, as I was saying, the nice thing about this topic of NTK is that even though we were only reading just the single original paper, and it has a lot of stuff in functional analysis, mainly in this case. Uh, since that paper, there's been a lot of work first applying computing the NTK for other architectures than just standard neural networks, and especially there's been the stuff by Greg Jang on tensor programs that goes a lot deeper into that and also uses some random matrix theory. So I expect that with this line of paper we can actually cover other things in math. So more content to come. Oh, and I need to uh, yeah, put this in focus. So yeah, the brief outline. So I'm trying to be fairly self-contained, so I don't assume that everyone has all the baggage in functional analysis and optimization, or mostly functional analysis in this case, to get through everything in the paper without being confused. So I'll be giving some reminders for other things. Note that I also needed a lot of these reminders myself, so it's more. So expect this to be self-contained and very explanatory, and I won't actually go into the proof because that's a terrible idea for a presentation, but let's see how it goes. So yeah, I'll start with some brief reminder about kernel methods mainly and also a bit of functional analysis. Then we actually delve into the main paper itself with how they derive the NTK and some of the theoretical results. I didn't have time to finish to add the numerical experiments they did for in their paper, but I can I can pull the paper on the screen and you can discuss that later. So yeah, so let's start with kernel methods. So I mean I said kernel methods, but I'm only really talking about kernel functions. So a kernel function on x is some arbitrary set, and a kernel function is some symmetric function kxx. So symmetric just means k of xy is equal to a of yx, k of yx, sorry. And let's say here it's from xx to the real number, and it satisfies this property that the sum of ci, cj, kxi, xj is greater than 0 for any x, so for any set of x I choose in my set x, and for any real coefficients r. But really, you can interpret this as saying, okay, if I take my xi's and form the matrix k with element ij, kxi, xj, that matrix is positive definite. And so positive definite matrices, especially symmetric positive definite matrices, have some nice properties that happen all throughout and both math and statistics, but especially in this area, we'll see a lot of them. So a kernel function is just a symmetric function, and a positive definite function, which is usually the type of kernel we care about, is one that satisfies this inequality. Now, if you have a positive definite kernel on your set, that automatically you get for free what's called a reproducing kernel Hilbert space. So a Hilbert space is just a space of functions on X. So I have functions from X to R. That forms a vector space that may or may not be infinite dimensional, depending on what X looks like. And it has an inner product. So this binary form that's the inner product that I can use to I can use it to compute angles, but then I can also use it to compute a norm. So I have a vector space with a norm, and I can do analysis with that. And the fact that it's a reproducing kernel Hilbert space means that this map kx, which is simply you can say it's carrying your kernel. It's a function in your space for any x in my set x, and that if I take the inner product of this kx with some arbitrary f in my function space, that's the same as evaluating f on x. And so one way to define RKHS is just it's a Hilbert space where the evaluation functionals are continuous or in my space. But the intuition is that when you, especially useful for machine learning, is kernel methods, they're essentially equivalent to taking your set X and projecting to some Hilbert space via some arbitrary feature map phi, which may or may not be nonlinear. And for in this case, so because we're map taking X, which may or may like it may be something arbitrary, maybe words or something with no structure at all, but I map it to a vector space, and automatically I get for free some Hilbert space and linear products between them. And the first application, and we'll come back to that. So a Gaussian process is something that does use kernel functions. So formally, or not so formally, I'm abusing notation a bit. A Gaussian process is some stochastic process. You can replace in your mind stochastic process with random function. So say x from some arbitrary space x to let's say the real numbers of dimension d, such that for any finite number of points I can sample in my space, so x1 to xn, if I form the vector of big X evaluated at all these points, this just follows a normal multivariate normal distribution with some mean mu which depends on these points and some covariance matrix sigma that depends also on these points. And you can think that okay, a Gaussian process is basically like a Gaussian distribution but over some function space. And so you can imagine that it's some other people in the paper they note it with the n for normal as well, but I'm noting it with GP for Gaussian process, where I have some mean function mu and some covariance function sigma, which takes values over the whole space. And note that this sigma, because it's a covariance matrix, it's actually a positive definite kernel in this case. So that's our first instance of kernel methods, or at least kernels appearing. That this won't be the last. So let's now we're actually moving a bit more into what the paper does. So the first thing the paper does is making a distinction between parameter space and function space. So usually in machine learning models, we have some models that depend on some parameters that usually we can say they live in some vector space, and they represent some kind of function. And usually we put the focus on the parameters, but in the paper they say, okay, let's actually look at, instead of the parameter, let's look at the actual functions being implemented by these parameters. And one sort of unfortunate thing is that this map from parameter to actual function implemented might not be injective. And especially for neural networks, there are tons of symmetries where different parameters basically map to the same, essentially the same function. But the nice thing is that we're sort of ignoring, by jumping to the function space, we're ignoring all these symmetries and these nasty stuff. And so right now we just say, okay, our function space is just a set of functions from R and 0, which are input dimension, to R and L, which is our output dimension. And the actual paper is a bit dodgy on this point. I'm a bit suspicious of this part, but we can define a semi-norm on our function space here, assuming we have some input data distribution, which may be some distribution, but usually it will be basically an empirical distribution from some data set, and it defines some inner product, so f of g with index p, so p in, which simply defined as the expectation. So this expectation here, where we're taking x, sampling from our input distribution, and evaluating essentially the inner product, but in the output space of fx and gx. So ignore this comment on the bottom because it's actually incorrect. But usually when people do functional analysis, they're a lot more careful about specifying what exactly what kind of functions go in there, and in this paper they don't. So it's a bit dodgy, or at least I find it a bit dodgy, especially since this thing it's an inner product, but it does not define a proper norm. The reason for that, especially in this case, is that because we're only evaluating on the data points, we cannot distinguish between like if I have two function f and g that are different, they don't have the same value everywhere, but on the data points they have always exactly the same value. So the difference will have norm 0. So as far as this thing is concerned, they're the same function, um, but but even though they're not. So this is why it's called a semi-norm. It's just a norm where it's not guaranteed that you can have vectors that aren't zeroed that have norm 0 or semi-norm 0. So keep that in mind. Oh yeah, one short slide about neural networks. I think everyone knows how they work. The one thing to pay attention to is how we parameterize them. So notice that all of our parameters will say that they come from just a standardized Gaussian distribution, and the weights will actually scale by 1 over the square root of the dimension of the layer. And this part, 1 over square root, is actually important rather than say 1 over n, essentially to ensure that we get the conversions to these nice limit objects as this NL goes to infinity. Which brings me to my first tangent. So I mentioned Gaussian process, I mentioned neural networks, and actually because I'm taking this Gaussian distribution over my parameters, that induces some probability distribution in my function space, and actually that distribution is a Gaussian process itself. So specifically, it's a Gaussian process with mean function 0 and some covariance function KL, which I won't show the computation here, but it will come up later. And one really nice thing is that already for this was concurrent work. It was concurrent work to the NTK, but the in the like before the 2000 there was a Radford McNeil that did a lot of work on this, and he had some really nice papers about showing this kind of limits of the priors of a function space induced by the priors over the parameters. So yeah, but in this case we already know that as the layer width goes to infinity, this covariance function here has a deterministic limit, and in fact it's closely related to the NTK, as we'll see. So yeah, the intuition for why we get a Gaussian process, even note that we get a Gaussian process even in the finite dimensional case. And the intuition for that is that the pre-activations of each layer, so before we apply the nonlinearity, this is a sum of Gaussian random variables, the variables being the parameters weighted by the input. And so when you have a sum of Gaussian random Gaussian variables like this with some weights, the output distribution is also a Gaussian. So that's the key intuition for why it works.
Is it the same deterministic limit no matter how deep the network is?
Um,
I.
Note that it does depend on the number of layers. So big L is the number of layers. So
Mm-hmm.
you're right that it's not. It does depend on the layer.
Gotcha. Or so are these the f theta is like one per layer? Like, or is it like is f theta referring to the entire network
Yeah,
or?
f theta means the just the output distribution after the L layers. But
Mm.
if you look at the what happens between the layers, you also get some Gaussian processes.
Gotcha. Okay, thank you.
And yeah, but usually the way to prove this is the same way as NTK does. Basically, you first show for one hidden layer that you get a Gaussian process, and then you add layer and say, okay, assume the output distribution of my previous layer is a Gaussian process, then by induction, the next one is also a Gaussian process. You continue. So yeah, so the other thing missing is that when you have a neural network, usually we try to optimize, train it to solve a problem or to approximate some function, or at least in this case to minimize some cost function C, which will be defined on our function phase, but usually it will only depend on the input distribution. And one problem we have in machine learning in general is that even though C might be a complex function in the function space, when we parameterize it with some FL, which is, remember, is our map from the parameters to the actual function, when we parameterize in this way and try to optimize this might not be a complex function, especially related to these nasty symmetries we can get for neural networks. So keep that in mind. Um, the one last piece I need before actually moving into the NTK is that, so let's define a multi-dimensional kernel. So it's a kernel function, but for with more dimensions. So we'll define this as a function that takes two inputs and it outputs a matrix, so R and L, where this is the output dimension. And this actually induces a bilinear map on our function space. So also almost an inner product, where we define it as the expectation of taking x, y in our input space or in our input distribution, and evaluating this thing here, which is simply also an inner product with a positive so yeah, positive definite matrix in the middle. And we'll say that k, the kernel k, is positive definite with respect to our semi-norm here. If the semi-norm positive implies that the k norm is positive. And so you can interpret this as saying that k might not be positive semi-definite, but if it is at least positive definite on our input distribution, so on xi, like literally form the matrix of k xi xj for all xi for all ij. If that matrix is positive definite, then we have this property. Okay, I small lie when I said this was the last thing. So um, F is our function space, and because it's a vector space, we can form what's called a dual space, which is the space of all functions. Or we can say so it's a set of linear functions from F to R in this case, and it has a nice relation to the original space. And in particular, for any mu in our dual space, which is a function that takes an element of f and returns a scalar, and is linear, we can actually find a function d in f such that applying mu to some f, a function, is simply taking this inner product. And in this case, note that because we have this empirical distribution that only evaluates this inner product on a finite number of points, um, so actually this dual space is, in effect, it is just a finite dimensional vector space, because we only care about the values of this d on our inputs, so on our training points. And technically you could do the same for f here, just saying, okay, I don't like this semi-norm, so let's just say that any two vectors that have semi-norm equal 0 are the same, and then you also end up with a finite dimensional vector space, but we have no reason to do that. Whoop. So second tangent. So of course there will be a lot of tangents for an NTK talk. So whenever we have a map F between two norm space, so vector space with a norm, F will say it's differentiable at some point x0 if we can find some linear map x, so L being a linear map from x to y, such that okay, this awful formula is satisfied. You can reinterpret it as basically L is like you're trying to have a Taylor approximation of f around x0. And so in the general function analysis case, this gets very hard to prove, and quite a lot of maps do not have a nice derivative, but when he does, we'll note it this way. So saying d, the differential of f evaluated at some point x0, and we think it's basically the Taylor approximation. And the special case when f is a map from x or a norm space to R, which is also a norm space in some way, then the derivative of that would actually be an element of the dual space because it's just a linear map from x to R. So now I have all the things I need to explain this maybe not so readable diagram. So remember, on the bottom we have the parameter space and the function space, and we have the thing that's the dual space. We're mapping. We can, for any element of a dual space, I can find some elements of my parameter space such that applying mu is the same as taking these inner products. And again, um, because because I cannot distinguish between functions outside of the training data set, I can have multiple functions that actually get mapped in this way, and we'll define some map phi k. So actually, I think, wait, did I? Oh right, I forgot this slide. Sorry. So apologies. So yeah, so the key thing is that say I have my kernel function and I take some I, then I can first evaluate. So curry x k is at some x. So this is a function. If you notice large part, this is a function that takes an element of x and returns a matrix. And if I now take just like a column of that matrix, that gives me a function that takes some x in my inputs and returns some an element of my output space. So this is a function of my function space, and I'll define this map from the dual space to f, and I take some dual elements to some new element f mu, and we'll define it as simply, okay, the ith element of f mu evaluated at x will simply be mu applied to my kix functional here, which should be simply this inner product. And so the key thing is that we now have a way to map from a dual element to a prime element, which um, we'll need to later to actually make the NTK. So yeah, this phi here is just my map from my dual elements to some phi mu, and specifically the NTK depends on what they call the kernel gradient. So the idea is that you take your sum f0 and you take the derivative of your cost functional, which remember the cost is a map from bf to r. So taking the derivative is an element of my dual space, and I map it back to my function space by applying this map phi k, and that is called the kernel gradient, which notice that it depends on this kernel. So depending on what choice of kernel I use, I will get different results. So yeah, we have another definition of again, the definition of the kernel gradient. So it's really taking some element 0, evaluating the cost, taking the derivative of the cost, and then mapping back to the function space. And this looks scary, but on an empirical data set, it'll just look something like this. So just this mean of kx xj and taking the derivative at xj. So remember that in effect my dual space is just a finite dimensional space. So this is basically just the gradient of my cost function evaluated at xj. Okay, so now we can talk about what happens when training a neural network using gradient descent. So we'll say that f of t follows the kernel gradient descent with respect to the kernel k if it follows this ODE. Note that the reason we're taking an ODE here is that it's sort of the infinitesimal step size or learning rate uh, limit of gradient descent as we use. So you can say that the gradient descent algorithm is just an approximation of the ODE, and using ODE makes things a bit simpler in the analysis. So yeah, we'll say that we have this differential equation within function space here, where the partial derivative of t of f is simply minus the kernel gradient of the cost. So this might not make a whole lot of sense because it's an ODE, or it looks like an ODE but in a function space, so that's fairly hairy things to get into. But at least we can say that the cost function, which is just a real number, this evolves as this. So we have essentially the derivative of the cost, and we take the inner product of the gradient kernel, and this is simply the norm, the k norm of my derivative remember the derivative of my cost at f of t. I think I think maybe I forgot to put a minus here because otherwise this would diverge. But yeah, so this would tell you okay, my cost function decreases, but this actually depends on my k. So if k is positive definite with respect to my input distribution, then I get for sure that f will converge to some critical point of c. So some point where a critical point being just some point where the derivative is zero. So we're guaranteed to decrease to some point where the derivative is zero. And if you add the additional assumption that C is convex and bounded below, then we know that F will converge to some global minimum. So that's nice because if you can show that our functional objective function is convex and that our kernel here is positive definite, that we're guaranteed to have convergence to some minima. And it's useful to show an example that does not necessarily involve neural networks in this case, and that's the one from the paper. So given some arbitrary kernel k, we can approximate it by sampling some random functions f of p or fp from a distribution that are covariance given by k. So here, let's assume we can sample from some Gaussian process that has this particular k as covariance, and we can define this random linear parameterization by simply taking arbitrary linear combinations of my fp. And if you want an example of this, random Fourier filter is actually an example of this kind of random function parameterization. And it does actually also relate to Gaussian processes. So if we apply taking the derivative with respect to some parameter theta p of my functional or function f theta, it does not depend anymore on theta, it's just 1 over square root of p then my function. And so if I optimize this with gradient descent, I get something fairly simple that looks basically like this. And so I think I had, whoops. So sorry, I get this equation which is fairly tame because it does not depend on theta, or at least it's reasonable to compute. And yeah, doing a bit of more algebra, I can sort of decompose into looking like this. And this is actually equivalent to gradient, gradient kernel descent with respect to the particular kernel being simply taking the derivative of my map from parameter to function and taking the derivative to each parameter. So if you want to think in feature space in the feature map way of kernels, that's just taking as your feature map the gradient of your model with respect to the parameters, which in this case it does not depend on the parameters, so this is a constant. And so the nice thing is that okay, I now have a gradient kernel descent with a constant kernel, so if I can show that this thing here is positive definite, then I ultimately know that I converge. And we actually can do literally the same thing for neural networks. So the sort of main, not quite result, but almost result from the paper is that for a neural network, the network function will follow the kernel gradient descent when optimized with gradient descent, or the parameters are optimized with gradient descent. Follow this, where the neural tangent kernel is basically exactly the same. We're taking the map from parameter to function space and taking the gradient of that with respect to each parameter. So in the end, it's not as scary as you might think. And note that we're mapping because this map here, we're just taking a gradient to with respect to parameters of some function. This is just a finite dimensional vector, so we're not even technically moving into infinite dimensional vector space in this case. But we are when we take the infinite width. So a brief moment to set up. So let's assume that all my layer widths go to infinity. and some minor condition on sigma. If you don't know what Lipschitz means, don't worry. You still have time to run. Um, but yeah, if I have this fairly nice conditions, then I know that my neurotangent kernel will convert to some actually an arbitrary limit, which is just a scalar kernel omega infinity, and taking the outer product with the identity. So maybe don't worry too much about that part. Just worry about this. And we actually have some nice equations to compute my limit. So for the input, because we don't even have any weights yet, it's just the input covariance distribution, and this one is actually the same as what happens in the neural network Gaussian processing. And then for the next layer, I just take my previous kernel and multiply it with this term here, which is simply an expectation of taking my input. So I'm taking f from the previous layer, and I'm taking the expectation of the derivative, so sigma prime, which is the derivative of my activation function, evaluated at these, and I'm taking this expectation, and I'm adding also the input to the input covariance, but for the same layer. So I have, I have them on the bottom, and those are actually the covariance of my neural net, the Gaussian process I mentioned before. So yeah, it's still just the input is just input covariance, and then for the other layers is just an expectation with respect to some Gaussian process with my activation function. So one important thing is that note that this limit here, it only depends on essentially my input distribution and my activation function and nothing else. Except maybe this parameter beta, but it just controls the bias, so it's not really important. So the key thing, and it's also the same conclusion for the Gaussian process, is that really in the infinite with limits, what matters is the activation function that determines what kind of prior or what kind of thing you'll get in the end. Oh,
So one, sorry, can you
yeah, go on.
like um so to be honest, I had never actually read the NTK paper because all I really knew, I guess I was only familiar with kind of the criticisms of it. And the main one that I heard again and again was that it doesn't actually correspond to um and I actually I did really enjoy and I found the paper very fascinating. So thank you for having us all read it. But anyway, yeah, the main criticism that I've heard time and again is that it doesn't actually correspond to what's happening in practice with neural networks because there's no feature learning. And I guess and I guess this is kind of that, this is kind of what that's saying is that if, say, you're doing, you're just giving you're just giving the model categorical vectors, because your data is tokens, in a or yeah, like sequences of tokens or something like that, and it's just these kind of one hot vectors, and um so what is the kernel like in that case? Like, what does this do instead of feature learning? It's just like the empirical covariance of your your one hot data, and that's kind of like the input kernel, and then the rest is just the expectation depending on everything else. Like, what? I don't know. Does this kind of make sense? Like, what?
So why the no feature learning, right?
Yeah, yeah. Why does the feature learning not really happen?
Right.
Why is just entirely constant based on the yeah.
Yeah, so yeah, you're totally right that the main drawback is that it, in this context there's no feature learning, and the
Mm-hmm.
reason for that is that because the contribution of any single waste is just very small, and that's actually
Mm-hmm.
the McNeil paper has a lot more interesting things about this because he also looks into okay maybe okay the problem with these priors or Gaussian priors is that we don't have features, but if we try this other prior, we have something that looks like features. But for in the NTK stuff, so indeed you don't get features, and that's sort of expected. As you like, remember, this is about what happens when you take your layer width to infinity, and in that
Mm-hmm.
regime, your network does not need to learn anything because it just has enough random, like because you're taking some random projection with or random dot product of vectors, you just have like an infinite vector of random features. Maybe most of them will do nothing, but a couple of them, or a couple of them, you have like a tiny little part of feature that you care about, and then the next layer will just combine them, and so like it's more each any single individual parameter has a very negligible negligible effect, but the
Mm-hmm.
combination of all these features sort of makes something happen.
I suppose maybe my question then is there any understanding of like what so if this is entirely, the kernel that you get is just based on, you know, the number of layers that you have and your data, like how drastically does the kernel depend on your data? Like, is there like a leave one out like kind of analysis of like how, if I have a data set and I remove one random piece, one random piece of data, um how like how much does the kernel change? like
Yeah,
like are there like,
I don't have
you
an
know
answer to that yet,
Okay.
but
Yeah.
relating to the feature learning, I know one of Greg Yang's paper is about yeah this NTK limit, but with actually feature learning. So that's like I know
Mm-hmm.
people have looked into okay having these infinite limits, but also having feature learning and
Yeah.
stuff like this. So
Okay.
but yeah, so back to your the question just before. Um, actually, can you repeat it again because I maybe didn't catch everything.
I mean, I guess my question just before is like, I actually, I guess I'm not like, no future learning. Like, this is clearly useless. But I guess it is, it's intriguing to me that this is so tightly connected to the data because something that I have been wondering about for a long time is, you know, sometimes neural networks generalize really well and sometimes they don't. Sometimes in your vision model you get these terrible spurious correlations that, you know, in practice mean you get these really unpredictable failure modes, or, I don't know, all sorts of stuff. And I guess I'm, I don't know. And I guess like one and so I guess I'm just intrigued by like, no, like this is entirely, like it makes sense that this is entirely really, you know based on the data that you have. But I just have lots of questions on like, is there a way to look at my data set and kind of tell whether or not the like, does the neural tangent kernel say that, oh, like you have a good data set that is really gonna, like there are some spectral properties of your data set that mean that the model will be able to learn it well and generalize well, or not, or like, there's something kind of defective and you have a bad test. I don't know.
Yeah, that might be the case. I mean, there you can indeed look at the spectral properties and learn a few things. But yeah, that's definitely things I don't have all the answers right now,
Sure.
but I'm willing to explore them in the future.
Yeah, yeah, yeah. Don't mean to put you on the spot or anything.
Yeah, no worries. So yeah, so this previous slide was the sort of the first main result of the paper, that we do have a static limit in the infinite layer width. Our second main result is that actually whenever we train the parameters with respect to some training direction, not necessarily the gradient one, but some training direction, so that basically includes most training algorithms we use. So yeah, following the update the parameters, following this descent in the function space. The only needed assumption is that so the integral from 0 to some t of the t is stochastically bounded. Stochastically is bounded in probability, right? So for any epsilon, there is some bound m such that the probability that this integral is greater than m is smaller than epsilon, something along those lines. And for example, if you know that the norm is like the norm of dt is decreasing, then automatically you get a bounded integral. So it's very easy to have in practice. So if we have this, then the we also get that the training will behave as if it were following the kernel gradient descent. Well, just the only additional thing is that we also still need the activation function to be Lipschitz, and we've bounded second derivative. But they mentioned that also in the beginning of the paper, that the assumption on the activation function seems to it seems like they can be relaxed in practice because it works for value, which is not differentiable, or at least it's almost ever differentiable. So maybe that's enough. So yeah, this actually result is actually nice because it means that the theoretical results apply not just for gradient descent, but for Adam and the other algorithm that people actually use, even in the stochastic sense. So the last thing we need, okay, we know that if we know that the kernel in the kernel gradient descent is positive or positive definite, then we have we know that we converge to some minimum, and we know that the NTK is already positive semi-definite. It might be zero, so the matrix may have some zero eigenvalues, but at least it's positive. And they mentioned that in order to get the positive definiteness, we need the span of the gradient. So yeah, take f theta and take the gradient that also gets a function in f. Take the span, the linear span of those, and if it's dense, so it's almost like a basis for this vector space, but with respect to the semi-norm. So if this is true, then we have the positive definiteness, and they link that to the fact that the pre-activation of the last layer, so the pre-activation of the last layer, they also appear in these gradient terms. And if you imagine, okay, you take a neural network and just ignore the last nonlinearity, well, we know that neural networks are universal approximators. We have some nice theorems for that. And so, for at least for many input distribution and activation functions, this is not a problem. We know that because of the universal approximation theorem, these span d theta will be dense in our function space, and so we'll have a positive semi-definite NTK. But I think probably one assumption about the PI, so the input distribution, is that maybe you're able to take more and more data points, and they cover your entire space density, so there's no region that have no data points at all. Not entirely sure about that point, but I'm assuming. So yeah, if there are no questions, I'll move on to the second example, which is least square regression. So let's assume that our class function is just the square norm between some f star, which is maybe what we're trying to approximate, and our f theta. And if we try to train that with gradient descent, well, okay, we have the NTK, and actually then it has a pretty nice form because the derivative of this is simply this linear term because it's a square. And so what ends up, it ends up with the thing that applying my map phi k to this whole thing just becomes a linear map times f star minus ft. So I get a linear equation, linear. So even though this is a linear differential equation in function space, it's a linear differ differential equation in function space, and those we know how to solve. And so we have we have an analytical solution being simply f of t is f star plus I have my term being the exponential operator, which we can define it this way, but it's basically we can think of it as just the map that takes my f0 and maps it to its state after time t, and we apply to f star minus f0. And note that because big pi here is basically this operator, um, I can sorry, um, it's a linear operator and it's a positive linear operator, so we know that this will have to go to like this operator will go to zero. So as we increase time, we get closer and closer to f star, and so now we can actually get into the spectral analysis. So if we are able to decompose this pi operator, which remember it might be in an infinite dimensional space, but if you can express it as just a spectral decomposition with respect to these lambda i's, which have to be positive or zero, and some eigenfunction f of I. So this is just your standard eigen decomposition, but with maybe an infinite number of terms. Then okay, I know that my exponential operator is just simply I think all my lambdas and then taking e to the minus lambda I. So those will convert to zero as well. And for a finite data set, actually this operator has finite rank. There's only a finite number of, uh, of eigenvalues, of non-zero eigenvalues, because my operator is just yeah a finite sum. And so this actually boils down to if you compute these eigenfunction, it's basically equivalent to performing the kernel PCA on your NTK kernel. Now, okay, I'm moving a bit fast on this one because it's maybe not essentially interesting, but I can look at my f star minus f0 and I can decompose it along each of my eigenfunctions. So this is my delta f is my the decomposition of this vector with respect to the kernel of pi, and then this is the decomposition with respect to the first, so to lambda 1, and then etc. to lambda n, so n and l. And so I end up with my f of d being, okay, my original f star, the projection to the kernel pi, so kernel just mean that this thing, pi applied to this thing is 0, so we don't really care about it, plus a sum of things that will go to 0 because my lambda i's are positive, so this decays exponentially. And actually we have a nice probabilistic interpretation of this, being that if we take the limit as t goes to infinity, we get something that looks like f of infinity is equal to f star plus my kernel term, and I can rewrite it as f0 uh, minus this term, and I can rewrite it again as f of infinity, the kth component evaluated at x, will be this kappa vector times this k inverse matrix, k being the gram matrix of my kernel, times y, and y is just my f star evaluated on my training data point. And so this looks like a bit like a regression, and actually it is. It's a kernel regression plus some center. So this thing here is, and this thing is just a centered Gaussian, so a Gaussian process. And so what this decomposition tells us is that as we go to infinity, we get, so one is the maximum a priori estimate from for taking fk a prior fk in a Gaussian process with the kernel. And so this thing is just a Bayesian estimate, or it's also the kernel regression estimate with respect to my star plus a centered Gaussian process. So in the end, it's just a Gaussian process with this mean. This is 0, and the covariance of this process is 0 at the data points. So they have a nice illustration of that in the paper actually. So maybe I'll show it. So yeah, we're finally at the end. We made it, guys. So the summary, at least the high level view, is that we can use this neural, but I'm putting neural because really the tangent kernel we can apply to any differentiable model, but it's mostly interesting for neural networks. And we can use it to describe how a model will evolve during training under gradient descent. The fact that we have a constant limit at infinite width, mostly it's interesting because it can prove that we have that the gradient descent will converge to some limit. But note there are some caveats with that because we're converging but with respect to this semi-norm. So because we can only look at our what our function does on the input dataset, we don't know how it behaves outside of it, and that the NTK does not tell you what it does. This is mostly determined by other factors like your, I guess, what you would call the inductive biases of your model architecture, because we know that okay, we will have some function that reaches a minimum, but there are potentially infinitely many functions in my parameter space that correspond to that. So this is a bit of like a skeleton that's being swept under the rug here. But the third nice thing is that we have now had a direct link between neural networks and kernel methods. Simply the interpretation that if you take the neural network and make it infinitely wide with this Gaussian parameterization, you're basically doing kernel regression. And which does come with the unfortunate thing that you're no longer in the regime where you have features, you're in the regime where you have just an infinite amount of random functions that you combine in a way that you get your output function. So yeah, we can discuss that point a bit later. So yeah, going further, so I mentioned that NTK, this was the original NTK paper, and as we discussed, there have been some criticism of it, but nonetheless, there's been quite a lot of work. So going further than that, so notably, people have computed the NTK for other architectures than the standard neural network, and I'd recommend maybe checking the series of tensor programs paper by Greg Yang and some other people on that, because they have this whole series of paper doing okay NTK for transformers, for GANs, for any other things, and then they go beyond. Another nice thing I've seen as an application of NTK is that if you take an architecture and compute its NTK, it itself depends on the depth. And so you can look at what happens as you increase the depth and maybe find the maximum effective depth for a given architecture. And so maybe after some depth, you find that your NTK is no longer positive definite. And so you know that if you try to make your architecture deeper than that, you won't be able to get some nice results. The other nice thing is that I've seen people trying to design activation functions to achieve some particular NTK. In particular, I think it was I don't remember where it came from, but they trained a network or look at the NTK for some known activation function and reverse engineer to find just a single activation function that lets them get that NTK, but for a single layer. But yeah, so those are some of the things that people have done with NTK, but there's a lot more.
Thank you so much. This was, yeah.
Yeah, it was actually a bit. It was tough for me as well. Like there was a lot of stuff, but I'm glad I finally read it in detail because I feel like have a better understanding of the certainly Gaussian processes, but some of the other details in the paper is nice. But I'm still quite a bit suspicious about the semi-norm thing. I'm a bit, but that's more
I
something.
mean, has any of the like follow-up work been, like tried to nail down what sort of function space this would actually correspond to, or is it just kind of like no one talks about it? Um,
I'd expect it's the latter because like this worrying about what kind of function space you're sitting in exactly is more of a reflex from actual people working in functional analysis where you really have to be careful about the actual space you're working with and the actual norm and all these details because it might mean that like for example one thing that might worry is like they assume that the sorry if I can find it back yeah like this step for example we say oh we can just take my kernel like this thing and it looks like a function from so it looks like a function in f so it must be in f.
hmm.
Usually people in doing functional analysis would be very suspicious of that being, are you sure? Have you verified that it is in fact an element of your space? Because it might not be. In this case, I think it is because we have this semi-norm that makes things very easy. But like, yeah, in general, the fact that this f here is not super well defined. I mean, I guess if you're just looking at the functions that you can implement with neural networks, you get at least some continuous or smooth functions. So you have
Hmm.
something, but I'm guessing they're not super bothered about what the actual content of this is because you have this semi-norm that sort of, in a sense, it brings it back to a finite dimensional space.
Yeah, yeah. I think I think part of the reason that I am so intrigued by this is like even if some of the details aren't quite right and we want to look at some other kind of extension of these ideas, but this I this kind of like universality of, to maybe abuse what is in fact a very technical term, but just like the fact that in decades of neural network research and what I'm sure are hundreds of different architecture proposals, you know, a bare handful seem to really make any difference in practice. Like, there's just so many decisions that you can make, and to really maximize performance on any given task or data set, you want to really pay attention to your activation function and all and the patch size, I don't know, all of these different
Yeah,
architectural details. But across most tasks, or across like a wide range of tasks, very little of that seems to matter. you know it there really does seem to be like all neural networks modulo you know some probably important details, but to a first order approximation, all neural networks are kind of doing the same thing. And and I think that I don't know. I guess that is why I'm so kind of intrigued by this and was so interested in it is just because like it seems to kind of give a justification for that idea that you know, truly most of these choices don't matter.
Yeah. I mean, I'd be very interested in looking at the actual tensor programs paper and like the maximum update parameterization, which seems to be
Mhm.
like a much stronger approach or much stronger version of the what NTK tried to do.
Yeah.
But yeah, definitely, I definitely think that like the problem with NTK is that it does not tell you how the your functions behave between your data points, or at least
Mm-hmm.
the results as they showed. So yeah, so I've pulled the paper here.
Mm-hmm.
Or okay, it's interesting because I had two versions of the paper. One which had so I think in the main results they yeah they have this proposition like in the original paper they did have this section, but then apparently they felt they had to add this section about okay, when we know that the data is distributed on the unit sphere, we know that the NTK is positive definite, and it seems like okay, it's that's not a super useful result because on the when am I ever going to get data that's nicely on a unit sphere? But I mean maybe in some
Mm-hmm.
cases. But so yeah, they do an experiment with this kind of data, and they show okay they show that the like you do in effect they get these conversions to the NTK, and they show also the sort of the output prior on that. So
Mm-hmm.
where you have so the blue is your yeah so the dash blue is your um, the like the Gaussian prior or like the limit I mentioned I showed with the like the kernel relation part and then the estimate. And so I think in this case it's basically like linear interpolation between the data points and then some 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 sorry Gaussian process in between. And
Mm-hmm.
like I think the biggest thing that this thing doesn't tell you, okay, how am I sure that I'm interpolating, or am I sure that? And I guess that would probably depend on the activation function. Am I sure about what happens between these data points? And that's I don't think NTK tells you about.
Mm-hmm.
But yeah, they do mention. I didn't mention it in the presentation, but they say okay, we can look at these kernel components, and that sort of gives you a justification for early stopping because the lambdas are positive. When I take this sorry this decomposition here, the largest lambdas, which are arguably the most important, they'll decay like before the others. And so if you identify maybe the most important kernel PCA components
Mm-hmm.
and wait until those have decayed and then the other you assume they're noise, that's essentially a form of early stopping. And yeah, they show. I mean, they don't exactly show that, but they show um, they show how the actual function decays along these principal functional components.
Mm-hmm.
But yeah, I know there's been people looking into the actual spectral properties of the NTK, but I have to track down the exact paper for that.
Something that I read like late last year, I got really interested in this body of literature that was looking that was I mean, I think that they were really fascinated by, you know, double descent and kind of like these different generalization properties of neural networks um and they proved relationships between like usually like one and two layer perceptrons and kernel ridge regression, and then we're able to use that connection to you know, on, you know, for certain classes of data, to, you know, be able to like derive analytic expressions for the entire training process and like the test loss and all of that stuff. And I kind of want to go back through that now and see.
Yeah,
I don't know, like
it sounds very interesting from what you described.
yeah, it's really good. I don't know if I'm brave. I mean, well, I'll look back at it. I don't know if I'm brave enough to present it, but I'll share some links in the channel and maybe we can talk about it. But it's very um it like on the one hand, my complaint about that work is that it's like, you know, it's always, you know, or most of it is very like they put kind of strict, properties on the distribution of the data set. But um but I do I don't know, I do like really appreciate uh people actually paying attention to the data on the other hand. But so yeah, now I want to reread those papers.
Yeah, it's definitely not the first time I've seen people linking neural networks and kernel methods because kernel methods are
Mhm.
better understood theoretically, and so they can like take some bounds or some result from
Yeah.
kernel methods and slap them on top of neural
hmm
networks.
I mean, especially it's just nice when
Sorry.
you know uh you have decades of prior work to draw on, and
Yeah, but then
you're
it's
like, oh no.
functional analysis, and you see that most people just sweep the skeletons under the rug
Mm.
and avoid just barely avoid some nasty demons. But yeah, I did want to
Mm.
shout out the McNeil paper on like Gaussian processes because it's I found it really nice to read, and also it has some really
hmm
nice, good explanations and also some pretty nice figures that show how the activation functions like impact what you get. So
hmm
like for example, it would be step functions, and this would be hyperbolic tangents. And yeah, I think in this case he does in this paper he does discuss about like the no features, the problem of no feature learning, and just mention okay that's basically an inherent problem of having these the parameters being Gaussians, and if we take like the parameters from a Cauchy distribution, we get something yeah like limits of power with infinite variance.
mm
I think yeah they get some more funky stuff. So yeah, I like definitely I would recommend reading the McNeil paper because like even though it's like from the Stone Age of 1984, it was a really interesting read and some fairly easy
Yeah.
to understand.
Yeah.
Okay, does anyone else have questions? I guess not. So maybe we can start discuss a bit what we're doing for the next time. So I don't know if you'd be up to do the second um,
Yeah, I think so.
representation theory.
Yeah, I think so. And I think yeah, focus on character theory and honestly probably just because it's interesting, the Fourier transform. Um and and so I'll look and I'll see tomorrow I'll post what people should read, but yeah, next week uh I can do some representation theory.
Okay, cool. Yeah, since people don't interact a lot, at least in chat right now,
hmm
if you have like some thoughts about maybe okay, what do you think about the fact of the idea of like alternating between different subjects? Because that's something we thought about doing, and here we tried it. Maybe a bit because of circumstances, but yeah, so we're trying something. So if you have some input about oh, okay, I like it or I don't like it. That's you can apply our RLHF to us and we'll maybe try to listen. So yeah,
And if there's anything that anyone wants to present, like I don't know, I'm always down to read a paper and then have someone explain it to me when I don't understand it. Uh,
yeah. I have a couple of like I made a couple of things on the sort of the GitHub repo, but I don't think many people have visited.
mm,
But yeah, I know at least for topics we definitely have more things we could cover in the NTK range or maybe the tensor programs. But those seem like quite a lot more work. I think some of them are like 80 pages and there's like five of them. So
yeah, but we'll figure something out.
yeah, and but the nice thing is that we can use that to get into random matrix theory,
Yeah, yeah,
which is going to be
that would.
another tough one.
Yes, yes.
Yeah,
All right. Well,
maybe we
thank you
should
so
start
much.
with GDL first. That would be the
All
easy
right.
one. Anyway, I think we can end it here.
Yeah, thank you so much. Really appreciate it.
Yeah, yeah, thank you and thank you everyone for coming, even though you haven't interacted much, but feel free to interact in the chat at least. So yeah,
Yeah.
thanks everyone, and see you
And
guys
and
next
there's
time.
no and also just in the yeah, like no such thing as dumb questions.
Yeah,
I
impossible.
I was confused reading this entire paper and so yeah, things
Yeah, so was
yeah.
I. It took me a lot of time to be sure. Okay,
Mhm.
what's the type signature of its subject? Okay, it makes sense at least. But
Yeah.
yeah. Okay, thanks
All
everyone, and
right.
see you later.